Students, today I'm going to teaching you MicroMaster in data science part 3, and I have already uploaded part 2 video, part 1 and part 2, and if you haven't seen it, then check the description box or check the playlist in data science, and you can watch or download there. And so uh, today the course uh, will be about sample spaces. So putting together a probabilistic model, and that is a model of a random phenomena or a random experiment, and involves two steps. First step, we describe the possible outcomes of the phenomena or experiment or interest. Second step, we describe our beliefs about the like likelihood of the different possible outcomes by specifying a probability laws. Here we start by just talking about the first step, namely the description of the possible outcome of the experiment. So we carry out an experiment. For example, we flip a coin, and sorry, uh, I will clearing your doubt step by step. Uh, don't don't hurry up. And so, for example, we flip a coin. Uh, Here is a coin, and it is head, and here is a coin, and it is tail, head and tail. So we flip a coin, or maybe we flip 5 coins simultaneously, or maybe we roll a die. Whatever that experiment is, it has a number of possible. So outcomes, and we start by making a list of the possible outcomes, or a better words, instead of the words list is to use the word set, which has a more formula mathematical meaning. So we create a set that we usually denote by capital omega. uh, the list of possible outcomes, and list of possible outcomes. The set is called the sample space, and is the set of all possible outcomes for of our experiment. The elements of that set should have certain properties, namely the elements should be mutually exclusive and collectively exhaustive. What does that mean? So uh, here is a box, and here is symbols and some probabilities symbols. So possible outcomes of our experiment, the elements of that set, that set should have certain properties. Mutually exclusive means that if at the end of the experiment I tell you that these outcomes happened, then it should not be possible that these outcomes also happened at the end of the experiment. There can only be one of the outcomes that has happened. So, uh, number one, mutually exclusive. Number two, list of list must be. Number two, collectively exhaustive, and number three, at the right granularity. So outcomes that had happened and being collectively exhaustive means something else, that together all of these elements of the set exhaust at the possibilities. So no matter what at the end, you will be able to point to one of the outcomes and say that's the one that occurred. To summarize, this set should be such that at the end of the experiment you should be always able to point to one and exactly one of the possible outcomes and say that this is the outcomes that occurred physically. Different outcomes should be uh, disti- distinguished in the sample space and corresponds to distinct point, but we say physically different outcomes. What do we mean? So we really mean different in all relevant aspects, but perhaps not different in irrelevant and aspects. Let's make more precise what I mean by that by looking at a very simple and maybe silly examples, uh, which is the following. Suppose that you flip a coin and you see whatever it result in heads or tails. So you have a perfectly uh, legitimate sample space for this experiment, which consists of just 2 point head and tails. Together, these two outcomes exhaust all possibilities. So, and outcomes, sorry, of the possible outcomes, and say that this is the outcomes that occurred, and physically different outcomes should be distinguished in the sample space and correspond to distinct point. I have already told you, and perhaps not different in irrelevant aspects. Uh, also, I have told you. So, which is the following? Supposed uh, that you flip a coin, uh, that is uh, no any option. That is no any options without a head or tail. So one time while you flip a coin, then probably it is it will be head one time or head two time, and it will be tail one time or tail two time or tail three time or tail four time, but not uh, any more aspects without head or tail. So another possible outcomes is head and no rain. So now, so this is a very legitimate samples space for this experiment. Now suppose that while you were flipping the coin, you also look outside the windows to check the weather, and then you could say that my samples space is really hard and it's raining. Another possible outcomes is head and no rain. Another possible outcomes it's tail and it's raining, and finally another possible outcomes is tails and no rain. This set consisting of four elements is also a perfectly uh, legitimate sample space for the experiment of flipping a coin. The elements of this sample space are mutually exclusive and collectively exhaustive. Exactly one of these outcomes it is going to be true or will have materialized at the end of the experiment. So which sample space is the correct one? The sample space, the second one involves some irrelevant details. So the preferred sample is for describing the flipping of a coin. The preferred sample space is the simpler one, the first one, which is sort of at the right guarantee uh, given what we have interested in, but ultimately the questions of which one is the right sample space depend on what kind of questions you want to answer. For example, if you have a theory that the weather affect the behavior coins, uh, then in order to play with that theory or maybe check it out and so on, then in such a case you might want to work with the second sample space. This is a common feature in all of science and common features in all of data science and science. So whenever you put together a model, you need to uh, decide how detailed you want your model to be, and the right level of details is the one that capture those aspects that are relevant and of interest to you. So let's go next questions, and some exercise examples. But first, uh, I'm removing this. And for the experiment of flipping a coin, and for its one of the following choices determine whether we have a legitimate sample space heads, and it is raining and heads, and it is raining tails. So so let's go next topic, sample space examples. So let us now look at some examples of samples spaces and sample spaces are sets, and a set can be discrete, finite, and infinite, continuous, and so on. Let us start with a simpler case in which we have a sample space that is discrete and finite. So let's start. So sample space, I will type here uh, samples, sorry, space. Uh, Sample space, discrete, discrete, sorry, discrete, finite example. So finite examples. So the particular experiment we'll be looking at is the following. We take a very special die at tetrahedral die. So the particular experiment we'll be looking at is the following. We take a very special die, a tetrahedral die. So it's a die that has four face numbered from 1 of 4. So first, uh, I'm removing, and we roll it once, and then we roll it twice again. We are not dealing uh, we're not dealing here with two probabilistic experiment. We are dealing with a single probabilistic experiment that involves two rolls of the die within that experiment. What is the sample space of the experiment? So, well, one possible representations is the following. We take note of the results of the first roll, and then we take note of the results of the second roll. So here I am creating a diagram. uh, Sorry. uh, sorry, it's my mistake, and yeah, I'm creating a diagram. And give some lines So it's a die that has four faces numbered from 1 up 4, and then we roll it twice again. So 1, 2, 3, 4, and uh, I'm making 4 lines. 1, 2, 3, and 4 line. So also I'm creating 4 lines. 1 and 2 and 3 and 4. So uh, this is 4, this is 3, and this is 2, and this is 1, and also this is 1, this blocks is 2, and this blocks is 3, and this blocks is 4. So x x is equal to first row as sorry, sorry, uh, x is equal to first row. uh, X is equal to uh, first roll, first row. X is equal to first row, and here y is equal to second row. So here uh, y uh, is equal to y is equal to second row. Y is equal to uh, second row. Okay, x is equal to first row, and y is equal to second row. Two rolls of a tetrahedral die. So we take note of the result of the first roll, and then sorry, uh, wait for a minute, wait for a minute. uh, so uh, we are dealing with a single probabilistic experiment that involves two rolls of the die within that experiment. And what is the sample space of that experiment? I have already told. Well, one possible representation is the following. We take note of the result of the first roll, and we have already taken it, and then we and this gives us a pair of numbers, I have already uh, done and of the little square in the diagram. For example, if the first roll is 1 and second roll is also 1, okay, the first roll is 1 and second roll is also 1. So for example, then this particular outcome had occurred. If the first roll is it 2 and second is it a 3, then this wait, for example, if the first roll is 1, first block and first roll is 1 and second second roll is 1, second roll is 1 and particular outcomes occur if the first roll is a 3, uh, first roll is a 3, sorry, if the first roll is a 2, if the first roll is a 2, wait for a minute. हल्का रुगा लागेको कारणले चाहिँ हाल ठिक छैन। Late. And so the first roll is 2. Uh, first roll is, sorry, uh, first roll is 2 and second roll is 3 and second roll is 3, 3, then this particular outcomes occur if the first roll is a 3 and next topic, uh, if the first roll is a 3, first roll, okay, first roll is a 3 and then the next one is a 2, then next 2, then this particular outcome occurs. Notice that these two outcomes are pretty closely related. In both cases, we observe a 2 and we observe a 3. Okay. So, but we distinguish those two outcomes because in those two outcomes, uh, the 2 and 3, the 3 happen in different order. The 2 and 3 happened different order. And the order in which they appear may be a detail which is of interest to us, and so we make this distinction in the sample space. So we keep the 3 2 and so we keep the 3 2 this 3 2 we keep the 3 2 and the 2 3. Okay, uh wait, we keep 3 2 and 2 3. So as a separate outcomes. Now this is a case of a model in which the probabilistic experiment can be described in phases or stages. So let me know, and we could think about rolling the die once and then going ahead with the second roll. So we have two stages. We have two stages. Okay, so I'm creating a sorry, I'm creating a map. Uh, First here and a line, and there is a line, and here is a line. So this is first, and this is second, and this is third, and also we'll put a line, and this is first, this is second, and this is third, and also we will put a line. This is first, and this is second, and this is third, and also sorry, uh, look here, uh, this is first, this is second, and this is third line. So also we'll put here, this is first, and this is second, and this is third. So here, uh, here we'll put also one line and also one line, and we'll put uh, also one line and one line. There is four line, and this is number one, and this is number two, and this is number three, and this is number four. So whenever we have an experiment with several stages, either real states or imagined states, so so this is one and one, one and one, and this is one and two, and this is one and three, one and three, and this is one and four. Okay, one and four, and here is last term. Uh, this is four and four, four and four. So So a very useful way to describe it is by providing a square sequential is providing there is uh, so a sequential description in term of a tree, and this is tree map. Okay, this is tree map. So a diagram of this kind, we call it a tree. It is tree tree diagram. Okay, this is a tree diagram. You can think of this as the root of the tree from which you start, and the endpoints of the tree, we usually call them the leaves. So we experiment starts uh, here is main point. Uh, here is main point. Here is main point. Okay, we carry out the first phase, which in this case in the first row. Okay, and we see what happens. So maybe we get a 2 in the first row and then we take note of what happened in the second row, and maybe the result was a 3. So we follow this branch here. We follow this branch here. Okay, we follow a branch. Uh, we follow branch by here, and we end up at this particular leaf, which is the leaf associated with the outcome 2 and 3. Okay, with outcome 2 and 3. Okay, 2 and 3. Notice that in this tree we once more have a distinct sum. The outcome 2 followed by a 3 is different from the outcomes. Okay, so if you didn't getting my topics, then uh, the outcomes 2, the outcomes I'm saying again, the outcomes 2 followed by 3 is different from the outcomes. Okay, and 3 followed by a 2, which would correspond to this particular place in the diagram. So 3 followed by 2. Okay, so this is 3 number, and 3 number is followed by 3 number is followed by 2, which would correspond to this particular place in the diagram. And in both cases we have 16 possible outcomes. We have how much? We have 16 possible outcomes. And similarly, uh, sorry, 4 times 4 max 16. And similarly, if you count here the number of leaves is equal to 16. So I'm removing it and wait for a minute. Give me a second. I'm removing it and I will explain you step by step. Okay, so just give me some time and I'm deleting it. And then also deleting this and sorry and uh sample space sample space continuous example. Continuous example. So uh sorry, I have mistaken the alphabet. It is not M, it is M. So enter and first number X and Y. X and Y, such that X and Y uh, such that X and Y such that 0 uh, greater division. So X sorry X and Y. Okay, so it is X and Y and X is Y and 1. So I'm creating a uh, blocks and so I have created a box and I'm creating a line here and one line here. Okay, so uh, this is Y arrow and this is X arrow. Okay, this is X and 1 and this is Y and this is 1. Uh, there was only 16 possible outcomes, but sample spaces can also be infinite. Uh, finite, and they could also be continuous sets. Here, here is an example of an experiment that involves a continuous sample space. Uh, Sample spaces. So we have a rectangular target, which is the unit square, and you throw a dart on that target, and suppose that you are so skilled that no matter what, when you throw the dart, it always falls inside the target. And uh, dart also, I have already told you, uh, which is the unit square, and you throw a dart on that target. So fall inside the target. Once the dart hits the target, you record the coordinates x. Okay, you records the coordinate x and y and y of the particular point that result from your dart throw, and we record x and y with infinite precision. So x and y are real number. Okay, I'm changing color. X and y, x and y, it is real number. So x and y, the particular point that resulted from your dart throw, and we record x and y with infinite precision. So x and y are real numbers. So in this experiment, the sample spaces is just the set of x y pairs that lie between 0 and 1, that lie between 0 and, oh, sorry, sorry, uh, it is showing a rectangle. So x and y pairs that lie between 0 and 1. Okay, so so exercise 3, presentations. So here is a questions. Okay, Paul check the weather forecast. If the forecast is good, Paul will go out for a walk. If the forecast is bad, then Paul will either stay home or go out. If he goes out, he might either remember or forget this umbrella. In the tree diagram below, identify the leaf that correspond to the event that the forecast is bad and Paul stay home. So, wait for a minute. Uh, uh, this is diagram. and one line, sorry, two line, uh, three line, uh, this is one line, this is two line, and this is the three line, and this is, sorry, and this is four line. Okay, so I'm solving a question that I have already told you. Sorry, I have already told you, and Paul checks, or uh, David checks the weather forecast. If the forecast is good, David will go out for a walk. Sorry, it is exercise. It is this is exercise tree. Okay, this is exercise tree representations. Okay, so I'm explain again. David checks the weather forecast. If the forecast is good, David will go out for a walk. If the forecast is bad, then David will either stay home or go out. If he goes out, he might either remember for yes sir, or forget his umbrella in the tree diagram below identifying the tree. The This is tree, okay? Sorry. Uh, this is tree diagram. This is tree diagram. Okay. The tree diagram below. The tree. This is tree and tree diagram here. Here, okay. Tree diagram here. Identify the leaf that correspond to the event that the forecast is bad, and David stays here home. So the question is, the uh, answer is number two. Okay, the answer is number two. Once again, I'm explaining. Once again, David checks the weather here and forecast. If the forecast is good, then David will go out for a walk. For the first forecast is bad, then David will stay home stay home or go out. If he goes out, he might either remember or for his umbrella in the tree diagram. In the this is tree diagram, identifying the leaf that correspond to the event that the forecast is bad and Paul stay home. So answer is number two. And we solve solution under a bad forecast. There are multiple scenarios, so a bad forecast must correspond to starting along the lower branch. Furthermore, if David goes out, there are two further possibilities, and there are two possibilities, number one and number two possibilities. Okay, number one and number two possibilities. Uh, there is two further possibilities, and these must correspond to leaves 3 and 4. The 3 uh, sorry 3 and 4. Therefore, the events of staying home must correspond to leave 2, and your answer is correct. So uh, uh, I'm ending this topic here, and so tomorrow I will upload a video which which topic is which topic will be probability axioms. Okay, so this video I'm ending this sorry chapter here, and we will uh, learn we will be learn sorry we will learn our next chapter tomorrow. Okay, so uh, give me permission give me permit to leave this chapter, and tomorrow uh, we will meet again, and thank you for watching this video, and stay safe and always learn, and you have to practice yourself. What did I say? What did I say? You have to practice yourself. If you want practice yourself, then you can't understand any topics you can't understand, because you have to prepare yourself. Okay, so if you have any doubt, then uh, you can inform me by comment section, or you can inform me by my Facebook ID. So